we can clearly see that a short, fat piece of tubing allows the fluid to pass at very little cost, very little pressure drop, very little inhibition of the flow, whereas a long, thin piece of tubing will inhibit the flow very significantly. Now, when we get into investigating electricity and the way different things act in a circuit, we will find that a piece of conducting wire, as long as it isn't too long or too thin, acts pretty much like a short, fat piece of tubing. It allows current to flow without much cost, without much inhibition. There's not much resistance to the flow in a piece of good conducting wire. This is good copper wire. It's kind of thin, but not too awful thin. Now, that's in contrast with a piece of resistance wire. This is a piece of nickel chromium resistance wire, and it's designed to have a higher resistance, so that this piece of resistance wire, even this little tiny end, this little tiny bit of resistance wire, would have much more resistance to flow than this long piece of conducting wire. And we kind of have to get used to that idea that a length of conducting wire doesn't interfere much with a circuit, whereas a length of resistance wire would. And we have thinner resistance wire. I'm trying to find the end of this so I can pull it out, and I'm not having a lot of success. Here we go. Okay, so that's a much thinner piece of wire. Okay, so that this resistance wire is made out of the same material as the other one that we just saw, but even a short piece of this resistance wire would produce more resistance than that whole long piece that I just showed you of the thicker resistance wire. And of course, a longer bit of resistance wire will create much more resistance than a shorter piece. We will have defined fluid resistance to fluid flow as flow rate divided by pressure loss, pressure difference. And that'll lead to a similar definition of electrical resistance. Now, this is a resistor. Okay, take a close look at it. It's short and fat, but the material that it's made of is much more highly resistive to the flow of current, so that we can adjust the nature of the material to make this as high resistance or as low resistance as we might wish, so that two resistors might look the same, but they're going to have a different, you can probably see rings of different colors. Those colors are part of a fairly simple code that allows you to look at the resistor and determine what its resistance is, because you can't tell from how long or how thick it is. And just as a short piece of resistance wire can have much more resistance than a long piece of conductive wire, a short piece of resistance material, even though it's quite fat, can have much more resistance than the nichrome wire. With a little experimentation, analysis of results, these analogies become very concrete. The analogy between fluid behavior and flow of electricity is not completely, well, it breaks down. It breaks down when you think, for example, why a long piece of tubing has more resistance than a short one. There is the decreased pressure gradient, but there's also the increased friction with the walls. In a conductor or a semiconductor or whatever, there's no analogy to the friction with the walls. It's simply the potential gradient is spread out. And the more spread out the potential gradient, the less flow you get. And of course, at the introductory level, we don't have to worry about that, but we do mention that there's not a perfect correlation with the between the two types of system.